Hello and welcome to my video on generator fields and all the other little coils that go around with a generator. The first thing we want to talk about is just a little real quick review, and that is generators themselves. We know they make electricity through electromagnetic induction, which is just simply the magic that happens when we have a conductor which moves through a magnetic field. And for our simple DC generator we're talking about, although these apply also to AC generators, the generator output is dependent upon either the length of the conductor or the speed that it moves or the strength of the magnetic field. And it can be any combination of these that can affect the output of the generator. Now let's take a look at our first case, the series wound generator, in this case, the field itself, the magnetic field, is in series with the load. Now we know from our basic DC theory that current in series is the same at all points. So how does this affect us with the series wound generator? Well, if our load goes up, there's more load, in other words, load current goes up. If the current through the load increases, we've added more of a load, in this case to our airplane, so our current through the load increases, then the current through the field will also increase. And in this case, if the current through the field increases, then our magnetism of the field will increase, and our armature output will increase. So what does that tell us with the series wound generator? The E output is proportional to the load. It's not going to be very stable. As our load changes, our voltage is going to go up and down. Not desirable. Series wound generators are not used in aircraft at all, and in a whole lot of other places. They're just a very special use, generally where we have a constant RPM and a constant load. Here's the shunt wound generator. Now you can remember from DC theory, shunt is also another word for parallel, and in this case the field is in parallel with the load. And if we remember from DC theory, our current in parallel is additive, which just simply means the current in this leg plus the current in this leg equals the current total. And that kind of makes sense, doesn't it? This armature is producing electricity, and some of it's going to go through here, some is going to go through here. And we know that the current is going to go through the path of least resistance. So in this case, what will happen if the load increases, the current through the load increases, obviously then the current through the field has to decrease because there's only so much current. In which case the current, or the magnetism, of the field will decrease, and that'll cause our E out to decrease. So here our voltage out is inverse to the current of the load. Now you might think with this that that's still not very stable. And the reason we use shunt wound generators is it's very easy to control the current in this path in the field to keep our voltage stable. So the shunt wound is what we'll do without any external regulation. The voltage out is inversely proportional to the current through the load. Let's talk about armature reaction. In a normal case, here is our generator common drawing that we see all of the time. And I've got my north pole and my south pole over here. And the lines of magnetic flux are just going from north to south. This is pretty common. And then our armature is not shown, but the armature would be right here in the middle of our generator. Now, let's add our armature to this. Now here, what's not shown is we still have our lines of flux, but the armature also creates a magnetic field. Why is that, you say? Well, the armature is just nothing simply but a conductor, right? A loop of wire. It's a wire, and there's current flowing through it, and current flowing through a wire creates a magnetic field. So in this case, we're going to have a magnetic field that rotates this way, and then one that rotates this way, as the armature itself is rotating around. The result we get is because of this magnetic field and this one, our magnetic flux from the north to south pole gets bent. And it gets bent where our old neutral plane was right here, right between them, and now the new neutral plane, where we want to do our commutating switching, is shifted over a little bit. This by itself would not be a problem. Why is this a problem, though? Remember, our current through the armature coil varies, right? The more load that I have on the generator, the larger current flowing through the armature. That's going to change the size of these magnetic fields. It's going to change the way the armature is shifted. The reaction, the armature reaction, will not be the same for all loads of the generator, and that is the problem. So what are we going to do about it? We're going to use interpoles. Interpoles are simply small coils, short windings. They're usually fewer turns than the main poles, and you notice they are wired in series with the armature. And the purpose of the interpoles is they're placed so they'll create a magnetic field that counters the armature reaction. And notice as the current through the armature, in other words, the load increases, the current through the armature has to increase, then this magnetism will increase, which will keep the armature reaction in check. That's the purpose of interpoles. You will find these in aircraft wiring diagrams, particularly of start generators. You'll see that there are interpoles. Larger turbine aircraft will have to have interpoles in their generator. The last thing we want to talk about real quickly is generator-motor reaction. So let's take a look at what we've got going here. And that is, now here are our two poles of our generator and one conductor of the armature right here. And we have our magnetism. In this case, it's going left to right. You can see that. And current flows through here. Now, when there's no current flowing through here, this armature piece is not making any magnetism, right? There's no current flowing through there. There's nothing happening. No problem. Now, let's look and see what happens once we actually start using this generator. So we've taken, again, we're just showing the one conductor of the armature, and we've connected it. The green line shows through a load. So we have current flowing through the external circuit and back through the armature. As this current flows through the armature, as we've already seen with armature reaction, it creates a little magnetic field. It's shown in red here, and the magnetic field will fight against our main field. And the more current that flows through here, the stronger these the field around the armature will be, the more it will fight. So what's the implication for this with the generator? Real simply, with no external load applied, it's very easy to spin a generator because there's no magnetism. But the more load, the heavier the load, the more current we're drawing, the stronger the magnetism through the armature, and this creates an actual physical, mechanical resistance to the armature spinning. This is really, if you think about it, just in keeping with the law of conservation of energy. I don't get to create this electrical energy through the load for nothing. The heavier the load, the more current I'm drawing, the harder physically, mechanically it is to spin the armature, the more power that it takes from the engine to move that armature. That's called generator-motor reaction. Well, thank you for joining me. I hope you learned something from this.